In problem set number 6, you will be implementing a fast parallel algorithm for seamless image cloning. Seamless image cloning is a modern algorithm for pasting one image into another in a very subtle way. And here's an example of seamless image cloning. So for example, you have a bear, a swimming pool, and with seamless image cloning, you now have a polar bear in the swimming pool. Our algorithm for seamless image cloning uses a technique called double buffering to iteratively compute a solution. The main idea behind double buffering in the context of this homework is that when store an approximate solution to a problem in one buffer, then we use that approximate solution to compute a better solution, which we store in another buffer. Then we go in the other direction, computing an even better solution and store that solution in the first buffer. After going back and forth many times, we will arrive at an ideal solution to our problem. This style of computation arises in many parallel algorithms, which is why we think it will make a really interesting homework assignment. Before we implement seamless image cloning, let's take a closer look at our inputs. We are given as inputs a source image, a target image, and a mask. We want to copy the mask value from the source image into the target image in a subtle way. To do this, we hardcode the values on the inside border of the mask region to be the same as the target image. Then, what we do is to solve for the unknown pixel values in the strict interior of the mask region. So how do we find these unknown pixel values in the strict interior portion of the mask image? We can do that as follows. First step, we will make a guess for the unknown pixel values, and that's called our initial guess, I0. I0 doesn't have to be a very good guess, so we can set I0 to be all zeros in the strict interior portion of our mask image. But note that 0 will be a very bad guess because it would not be very subtle, and it also will not conform to the source image very well. Now suppose we are given a guess solution ik to our problem. We can compute a better guess ik plus 1 as follows. For some pixel small I k plus 1 in big I k plus 1 in the strict interior region of the mask, we can compute the value of small I of k plus 1 as a plus b plus c divided by d. And let's go through each of a and b and c and d one at a time. A is the sum of ik's neighbors. We don't include ik in the sum, and we only include ik's neighbors if they are in the strict interior portion of the mask region. B is the sum of t's neighbors, where t is the corresponding pixel value in the target image. And the target image in our case is the swimming pool. And we only include t's neighbors if they are in the inside border of the mask region. And C is the sum of the difference between S and S's neighbors, where S in this case is the corresponding pixel value in the source image, and the source image in our case is the polar bear. And finally, D is the number of ik's neighbors, and ik's neighbors can be less than 4 if ik is on the border of the image.